We've been discussing virtual memory in somewhat generic terms, and I'd like to spend a little bit of time talking about the nuts and bolts of how it works under the hood. We're going to start by spending a little time talking about address translation just in very general terms. We know that there's two address spaces involved that we call the virtual address space and the physical address space. So we're going to use V to represent the virtual address space, and it's just a sequential set of values from 0 up to some value n minus 1. And that's going to be mapped to a physical address space, which we'll call P, and that's similarly a sequence of addresses from 0 up to m minus 1. It's important to note that m and n do not have to be the same thing. In particular, the virtual address space is often going to be much, much larger than the physical address space. The physical address space is literally limited to the amount of memory we have in a particular computer, whereas the virtual address space is not subject to that limitation, and in many ways that's kind of the point of virtual memory. We get to operate our programs in the virtual address space and then map in those portions of the virtual address space to physical memory depending on the currently executing code. And as we saw last time, the fact of locality is what allows that to be a fairly efficient way to operate a program in a larger address space than we physically have memory for. The translation between virtual and physical memory is really just a mapping, as I'm showing here, a mapping called M that takes the virtual address space into the union of the physical address space and an empty address that I'm showing here as the empty set symbol. For some virtual address A, we'll see that in most cases the mapping of A is going to give us a value A prime that's going to be part of the physical address space if the data at the virtual address A is in physical memory at address A prime. In some cases, however, we may end up with the mapping of virtual address A giving back an empty value, and that's an indication that the virtual address A doesn't have a corresponding physical address in DRAM. It might be an invalid memory request, or it might be that that information is still stored on disk, in which case we have to fish it out of the disk system into memory in order to be able to satisfy the request for that mapping. There's some new terminology here that we're going to want to be aware of, and I'm going to cover some of it right now and then introduce some of it later. But I'm going to use this little cheat sheet to remind you what some of these things refer to. So first of all, we've seen already that N and M are the sizes of the virtual and physical address spaces. And as you remember from last time, those are going to be powers of 2, so capital N, the size of the virtual address space, is going to be the power of 2 to some small n, which basically is going to translate into the number of bits necessary to access values in the virtual address space. And a similar thing holds for the physical address space, except now we're defining capital M to be equal to 2 to the power little m, and that little m is going to be the number of bits necessary to access any given value in the physical address space. We're going to also see that when we're thinking about the virtual versus physical addresses, we're going to partition the addresses in a way that's kind of similar to what we did to split up addresses to use in caching. In particular, there's going to be a page number, which is going to be the uppermost bits, and then within a page, there's going to be an offset in that page. This is quite like the notion of a buffer offset in the caching scheme. We identify a particular set and then find the matching buffer in the line that matches the tag, and then we use an offset to index a particular location within that buffer. We're going to do a similar sort of thing here in the mapping between physical and virtual addresses. We'll also see one invariant here, that the physical page offset, in other words, how many bytes we need to move forward in a physical page, is going to be equal to the virtual page offset. So here's an illustration of how that translation actually works. Here at the top, we've got a virtual address that we're translating. You can see that this has n bits from 0 to n minus 1. And we're trying to translate that virtual address into a physical address here at the bottom of the page. And you can see that this has m bits in it from 0 to m minus 1. And we're going to make use of the page table that we described in the last video. The idea here is that we're going to split the virtual address and the physical address into two pieces in the same way that we partitioned addresses when we introduced the idea of caching. The uppermost bits are going to be the VPN, which we can use our cheat sheet here to realize is virtual page number. And then the lower bits in the virtual address are going to be the virtual page offset. So what we're trying to do is find a particular page in the virtual address space, and then within that page we want to be able to access a particular sequence of bytes at some offset from the beginning of that page. So the virtual page number is going to be used to index into our page table. This is just a small representation of a much larger table in memory, but it gives you the idea about what's going on. This is kind of like a set index in that it's going to pick out an entry in the page table based on indexing through these entries. So if we imagine that the current virtual page number selects this entry here that I've highlighted, we are going to look in here and see that the valid bit is set, and then read out the physical page number from the page table. Again, the page table's job is to map from a virtual address into a physical address. So we're starting by just taking the top part of the virtual address, indexing into the page table, and what's stored there is going to be the corresponding page in physical memory. So we're going to grab that value and use it to formulate the first part of our physical address. Given that, then, we know which page of physical memory we need to access, and the remaining question is, which bytes within that page do we want to get? And as I mentioned before, this page offset on the virtual side and the page offset on the physical side are basically an index into that block to the first byte that we want to start fetching from that location. We also saw here in the cheat sheet that the virtual page offset and the physical page offset are the same. So we're going to just take these bits and copy them into the physical address, and that's going to form the address that we're actually going to go out to memory and bring in. The other thing that's illustrated here is this PTBR, which stands for Page Table Base Register. This is just a single address that's maintained by the kernel for each process in the computer that refers to the location of the first entry in the page table. So when the memory management system is trying to look up information from the page table, it's going to rely on this value, which is an address or a pointer to the page table, to tell it where to go look. And it's going to use the virtual page number as an index from this address to index into the table to find the appropriate entry and read out the physical page number. Something that's important to keep in mind when you're thinking about how this is working in practice is that the page table is stored in memory. So when the memory management unit is trying to identify a mapping between a virtual page number and the corresponding physical page number by looking it up in the page table, that requires memory access. It's also the case that on a machine with caching, like any modern processor, the page table entries will be cached just like any other memory access that's taking place on the processor. Remember that the memory management unit is on the chip, and it's reaching out to main memory in the same fashion that everything else is. So memory management wants to fetch a value in from a page table. That's going to use the same access mechanisms that the ALU might use to request an operand for an arithmetic operation. Let's consider the behavior of the virtual memory mapping process here in the case where we have a page hit. In other words, where there's already a physical page that's been brought into memory that corresponds to a virtual address that the processor is asking for. So the first step here is that the CPU is going to issue a memory request. And as we've seen previously, all of the addresses that are used by the CPU are actually virtual addresses. So it's in the virtual address space, and that's handed off to the memory management unit to fetch the corresponding value for that virtual address from the proper location in physical memory. So the memory management unit, as its first step, is going to request from the memory system the page table entry at a particular address. Again, that's just an ordinary memory request. It will maybe hit the cache if the entry is already in the cache someplace, and if not, it'll eventually go out to main memory to try to find the page table entry at that address. The memory system returns that page table entry back to the memory management unit, and then the MMU uses the data in that page table entry to construct the physical address as we've just been discussing. And then it finally issues a request for that physical address back to the memory system, which again could hit in cache or require a trip out to main memory. And then that value is going to be retrieved back and made available to the CPU, satisfying the request. The process is a little bit more elaborate in the case of a page fault. So this is the case where the processor requests a virtual address. The memory management unit attempts to find the corresponding physical page in memory, and it fails to find it there. So some similar steps here up front. Step 1 has the CPU sending a virtual address to the memory management unit, which proceeds as before to request from the memory subsystem the page table entry at the appropriate address. And then the memory system returns that page table entry, except this time the page table entry indicates that the requested page is not currently available in memory. This is going to cause what's called an exception, and that exception is going to do two important things. First of all, it's going to temporarily suspend the execution of the currently running process. Obviously, because the process is trying to access memory that's not currently loaded into the machine, it can't continue, so the operating system is going to temporarily suspend its execution until such time as the memory that's been requested is available. The other thing that's going to happen in the operating system is the MMU is going to trigger execution of what's called the page fault handler. This is a portion of the kernel that's responsible for dealing with this case of a request being made to a virtual address that's not currently in physical memory. Two steps that the page fault handler is going to have to deal with. One is to figure out where is it going to load this new page into memory. Now, if there are available pages in memory, that's not a troublesome thing at all. It can just say, there's a free page, let's go out and load that page in. But if there are no free pages available in memory at this point, the page fault handler has to decide which of the pages that are currently in memory it's going to evict and push back out onto disk in order to free up space. So step 5 here is indicating that the page fault handler did not find any free space in memory, and it pushed some page that it selected back out to disk. And the second thing it does is bring in the page that corresponds to the memory request that's being made and stores it in memory at the location that it freed up for that new page. Once that's complete, the operating system will reschedule the process that caused the exception initially and basically restart the exact same assembly language instruction that it was executing when the memory fault took place. So what I'm showing here as step 7 is really a recapitulation of step number 1. The CPU once again is going to issue a request for that same virtual address, and the process is going to continue, this time because the page of interest has been loaded into memory, will presumably result in the actual value at that address being sent back to the CPU. So this is all fine and good. What could possibly be wrong? Well, here's the issue. We'd like to make this address translation thing happen really quickly. Every single memory reference from the CPU cores is going to be a virtual address, which means that every time we want to access memory, we've got to do a mapping from a virtual address into a physical address. So we want that to be as fast as we possibly can make it. The problem is that those page tables are currently stored in memory. Now, we're going to get a little bump, actually a considerable bump in performance, because like any other memory access, those page table entries are going to end up in cache. But even if they get into cache, they're still subject to being evicted by any other data references that happen to conflict with them. And even if they're in cache, we still have to pay a slight delay to get stuff out of L1 that's going to reduce the overall performance of our program. So the solution to this problem that's commonly employed is to introduce what's called a translation look-aside buffer. It's kind of a mouthful, but it's also just referred to as a TLB. Basically, we're going to use the same ideas that we employed to design the main caches in the CPU to make it fast to convert a virtual page number into a physical page number so that we can go out to memory and fetch information in for the processor. The TLB is really just a set associative cache that's located directly inside the memory management unit. So when the MMU is given a virtual address by the processor, the first thing it's going to do is try to go find the mapping to the physical page right inside the TLB. If it can, then it can basically issue the memory request immediately out to main memory to fetch in that value for the CPU. On the other hand, if it can't, it's going to do the same process that we just described, whether it's a page hit or a page fault, and then update the TLB to have that new entry. The TLB is basically mapping these virtual page numbers into the physical page numbers. As the process executes, we're going to start to accrue the page table entries for those small number of pages that are being accessed frequently. In other words, locality is going to be our friend in this case, just like it was for the other type of cache. Here's an illustration of what the TLB looks like. So this should be quite familiar looking to you from the discussion of caches. Again, this is a set associative cache. So here I'm showing a cache with 2 sets, and then each of those sets has 2 lines in them. The similar kind of division is made in the address. Again, this is the virtual address that we're dealing with because we're still on the chip inside the memory management unit, and the MMU is trying to decide how to map the virtual page number into the corresponding physical page number. As with the other set of associative caches we've discussed, we want to split up the portion of the address that's going to be used to look stuff up in the cache into a couple of sections. One, which is going to be the lower set of bits here in the VPN portion of the virtual address, is going to select the set. In the case of this really simple TLB design, I've only got 2 sets, so really we'd only need to have a TLBI that's a single bit. So that's going to choose a set such that if the VPN portion of the virtual address is in the cache, it's going to be in that set. So let's assume it's this set. Then we're going to use the topmost bits of the VPN portion of the address as a tag and look up in any of the lines in this particular set to see if that tag matches. If so, and the valid bit is set, then we can read directly out of cache the page table entry for this particular virtual page number. This will give us all the information then that the MMU needs to be able to issue the physical address request out to memory to satisfy the corresponding virtual address request that's been made by the processor. Let's take a look at some of the assumptions that we're making about page tables. So far we have just a single page table in our architecture that's going to give us information to map virtual page numbers to physical page numbers. Let's think about that in a little bit more detail. So let's just suppose that we have 4K pages. In other words, they're 2 to the 12th bytes wide, and that we're working in a 48-bit address space. Now, if you think about how much space you're going to be taking up for page tables in that architecture, you can figure it out as follows. We know that there's 2 to the 48th addresses in our address space, and we're going to split those up by 4K pages. So we can divide that 2 to the 48th by 2 to the 12th, or multiply it by 2 to the minus 12th. And then we're going to have 8-byte page table entries to be able to store the appropriate information for the mapping. So we're going to multiply again by 8. If we add up the exponents here, we end up with 2 to the 39th bytes that are necessary for our page table. Now that means we're going to have 512 gigabytes to store just our page table, which is probably not going to be a realistic design choice. Our solution, instead of having to allocate one giant table that could take care of any possible mapping from a virtual address to a physical address, is to take a multi-level approach. So we're going to split up the page table into 2 levels. So the first level, which is going to be accessed first by the MMU, is going to take the page table entries and point to another page table. And this first level page table is always going to be in memory, but because it's pointing to a second layer of page tables, it doesn't have to be 512 gigabytes. Then that level 2 page table is going to finally refer to an actual page in memory, the physical page that the processor is trying to access by issuing a virtual address. And those second level pages can be paged in and paged out of memory like any other page. So we only have to pay the permanent residence price for the top level page table, and then the second level page table will give us a lot more flexibility to utilize memory efficiently and avoid this problem of having a ginormous page table. Here's an illustration of a 2-level page table. The first level is a single page table, and we can see here that it's got 1,024 entries numbered from 0 to 1023, or 1K entries. But instead of storing the actual page table entry data in the level 1 table, what we're going to do is use it to indirectly reference a second level of page tables where that information is actually going to be stored. And I'm showing these as also 1K entry page tables. So if I'm trying to look up a particular entry in the page table, I'm going to first reference the entry in the level 1 table. That's going to point me to a level 2 table, and then within that I can reference further down to come up with the actual mapping for the particular virtual address. And you can see that a little bit more clearly here if we also look at this third column, which is the virtual memory space. Let's say that we're trying to access the location of physical memory that corresponds to a virtual address issued by the processor to something in this page, page number 1024. The MMU knows that the size of each of the page tables is 1K or 1024, which are going to, and again, be numbered from 0 to 1023. So it can just do some simple math to figure out that the mapping for virtual page number 1024 is going to have to be in the second of the level 1 page tables, right? The first level 1 page table is going to refer to a level 2 table that deals with virtual memory page numbers between 0 and 1023, which means that the second one in level 1 is going to point to a page table that deals with the next 1K virtual memory addresses from 1024 to 2047. And then the third one would point to an intermediate page table that started at location 2048. By just being aware of the size of the various levels of the page tables, the MMU can do that calculation to identify which of the entries in the level 1 page table to look up in, and then follow that to the level 2 and eventually find the information for the physical page number in the level 2 page tables. This example also illustrates kind of the way a Unix process would be allocated in memory, in virtual memory. You can see here that at the low addresses in the virtual address space, we've got 2,000 pages allocated for, say, the program code and static data for our program. And the upper addresses are actually allocated for the use of the stack. Remember that we saw that the stack grows down toward lower addresses in memory, and the heap grows up from lower addresses toward high memory. And this illustrates how that's going to be placed into memory. Let's work backwards from this block that was allocated to store the stack for this process. We can see it's at offset 9215 within the virtual memory space. It turns out that that particular virtual memory location is going to be found in the 9th level 1 page table entry, which is going to correspond to a new level 2 entry, and then it's going to be the very last entry in this level 2 entry that corresponds to this 9th block of 1K virtual page numbers. We can also see that we've left unallocated here for growth in the heap and in the stack 6,000 unallocated pages. Those come from these 6 entries here, which don't have anything associated with them in the second level page table. They're empty. That basically provides the illusion that we've just got a whole bunch of empty space here, although because we're now using a multi-level page table, we don't have to actually allocate all 6,000 of these unused page table entries. We just leave the first one blank and don't ever allocate anything for level 2. And then the final 1023 unallocated VM pages in this region correspond to the page table entries that are in this part of the level 2 entry that is really at this point only being used to refer to a single virtual page number for the stack. It's interesting to take a look at how we would partition the virtual page number portion of the virtual address in order to be able to access this K-level page table. So I've generalized here in this illustration to K levels instead of just 2. And you can see that the portion of the virtual address that's normally got the virtual page number in it, I've now partitioned into multiple smaller segments. And each of these smaller segments is going to be used to index into the page table at a particular level in the K-level table. We'll take the first portion of the virtual page number and we'll use that to look up a location in the level 1 page table, which is going to point us to the level 2 page table. Within that one then, we're going to use the second portion of the virtual page number to index into this second level page table, which is going to point us to the next page table. And eventually we're going to end up here in the final page table at level K, where we'll actually now finally find the physical page number that corresponds to this entire virtual page number. We can then drop that down into our physical address that we're trying to create, grab the virtual page offset and copy it in as the physical page offset, and that's the physical address that we can use to go and access the memory that corresponds to this virtual address. In summary then, from the programmer's point of view, virtual memory has lots of advantages. One is that each of our processes is going to run in its own private address space, which simplifies kind of how we compile and link and reason about our process. And it's also protected from access from other processes. Each process running in the Unix machine is going to have its own virtual address space, identical to all the others, but because the address space is maintained and secured by the underlying mechanisms in the virtual memory system, we're unable to access or modify the contents of any other process. So it just makes for a much more reliable system overall. From a system point of view, it allows the system to make really efficient use of memory. It's going to basically treat the entire physical memory as a giant cache that's going to store blocks of the virtual memory space in physical memory. And because it's using this caching approach, it's going to be able to make use of the memory very efficiently. There's not going to be a bunch of wasted space occupied by information that can't be used or that isn't being used presently. Finally, it's important to keep in mind that all of this works only because of locality. If we didn't have locality in our programs, either spatially or temporally, Caching wouldn't work, the MMU would be super slow, we wouldn't be able to implement the translation look-aside buffer, we'd constantly be swapping information in and out from disk to memory and vice versa, and our software would all come to a crawl. So as you can see, locality continues to be one of the really, really important ideas in computer architecture, arguably one of the most important ideas in all of computer science.